So we've just talked about randomized algorithms, but we can look at the probabilistic analysis of algorithms, and that gives us an opportunity to step back and, as we said, everything we've been talking about is worst case analysis.
Right.
Could you maybe comment on the usefulness and the power of worst case analysis versus best case analysis, average case, probabilistic? How do we think about the future of theoretical computer science in the kind of analysis we do of algorithms? Does worst case analysis still have a place, an important place, or do we want to try to move forward towards kind of average case analysis?
Yeah.
And what are the challenges there?
So if worst case analysis shows that an algorithm is always good, that's fine. If worst case analysis is used to show that the solution is not always good, then you have to step back and do something else to ask, how often will you get a good solution?
That's just to pause on that for a second. That's so beautifully put, because I think we tend to judge algorithms. We throw them in the trash the moment their worst case is shown to be bad.
Right, and that's unfortunate. I think a good example is going back to the satisfiability problem. There are very powerful programs called SAT solvers, which in practice fairly reliably solve instances with many millions of variables that arise in digital design or in proving programs correct and other applications. And so in many application areas, even though satisfiability, as we've already discussed, is NP-complete, the SAT solvers will work so well that the people in that discipline tend to think of satisfiability as an easy problem. Mm. So, in other words, just for some reason that we don't entirely understand, the instances that people formulate in designing digital circuits or other applications are such that satisfiability is not hard to check. And even searching for a satisfying solution can be done efficiently in practice. And there are many examples. For example, we talked about the traveling salesman problem. So just to refresh our memories, the problem is you've got a set of cities, you have pairwise distances between cities, and you want to find a tour through all the cities that minimizes the total cost of all the edges traversed, all the trips between cities. The problem is NP hard, but people using integer programming codes together with some other mathematical tricks can solve geometric instances of the problem where the cities are, let's say, points in the plane, and get optimal solutions to problems with tens of thousands of cities. Actually, it'll take a few computer months to solve a problem of that size, but for problems of size 1,000 or 2, it'll rapidly get optimal solutions, provably optimal solutions, even though, again, we know that it's unlikely that the traveling salesman problem can be solved in polynomial time.
Are there methodologies, like rigorous systematic methodologies for, you said in practice. In practice, this algorithm runs pretty good. Are there systematic ways of saying in practice this runs pretty good? So in other words, average case analysis. Or you've also mentioned that average case kind of requires you to understand what the typical cases, typical instances, and that might be really difficult.
That's very difficult. So after I did my original work on showing all these problems to be NP-complete, I looked around for a way to shed some positive light on combinatorial algorithms. And what I tried to do was to study problems, behavior on the average or with high probability. But I had to make some assumptions about what's the probability space, what's the sample space, what do we mean by typical problems? That's very hard to say. So I took the easy way out and made some very simplistic assumptions. So I assumed, for example, that if we were generating a graph with a certain number of vertices and edges, then we would generate the graph by simply choosing one edge at a time at random until we got the right number of edges. That's a particular model of random graphs that has been studied mathematically a lot. And within that model, I could prove all kinds of wonderful things, I and others who also worked on this. So we could show that we know exactly how many edges there have to be in order for there be a so-called Hamiltonian circuit. That's a cycle that visits each vertex exactly once. We know that if the number of edges is a little bit more than n log n, where n is the number of vertices, then where such a cycle is very likely to exist, and we can give a heuristic that will find it with high probability. And we got the community in which I was working got a lot of results along these lines. But the field tended to be rather lukewarm about accepting these results as meaningful because we were making such a simplistic assumption about the kinds of graphs that we would be dealing with. So we could show all kinds of wonderful things. It was a great playground. I enjoyed doing it. But after a while, I concluded that it didn't have a lot of bite in terms of the practical application.
Okay. So there's too much into the world of toy problems.
Yeah.
Okay. But all right. But is there a way to find nice representative real world impactful instances of a problem on which to demonstrate that an algorithm is good? So this is kind of like the machine learning world. That's kind of what they at its best tries to do, is find a data set from like the real world and show the performance. All the conferences are all focused on beating the performance on that real world data set. Is there an equivalent in complexity analysis?
Not really. Don Knuth started to collect examples of graphs coming from various places. So he would have a whole zoo of different graphs that he could choose from, and he could study the performance of algorithms on different types of graphs. And
but there it's really important and compelling to be able to define a class of graphs. So that the actual act of defining a class of graphs that you're interested in, it seems to be a non-trivial step if we're talking about instances that we should care about in the real world.
Yeah, it's there's nothing available there that would be analogous to the training set for supervised learning, where you sort of assume that the world has given you a bunch of examples to work with. We don't really have that for problems, for combinatorial problems on graphs and networks.
There's been a huge growth, a big growth of data sets available. Do you think some aspect of theoretical computer science, I might be contradicting my own question while saying it, but will there be some aspect, an empirical aspect of theoretical computer science, which will allow the fact that these data sets are huge, we'll start using them for analysis? Sort of, if you want to say something about a graph algorithm, you might take a social network like Facebook and looking at subgraphs of that and prove something about the Facebook graph and be respected, and at the same time be respected in the theoretical computer science community.
That hasn't been achieved yet, I'm afraid.
Is that P equals NP? Is that impossible? Is it impossible to publish a successful paper in the theoretical computer science community that shows some some performance on a real world data set? Or is that really just those are two different worlds?
Well, they haven't really come together. I would say that there is a field of experimental algorithmics where people, sometimes they're given some family of examples. Sometimes they just generate them at random and they report on performance. But there's no convincing evidence that the sample is representative of anything at all.